Allô? Ouais, c'est bon. Merci. Okay, please take your seat. We will resume the session. Okay. First, I have an announcement. I've been told that there will be a photograph to be taken at 12:30. You go out of this hall, you turn left, and you go outside the hotel, where the exhibition is. There's a big circle where the exhibition is, and you move into the center of the circle, and you look toward the hotel, and the photograph will be there probably, and we'll take the picture. So don't forget at 12:30, after the session, to take the picture. I will remind you that also at the end of the session. Okay, now we are moving toward EuroCirCol session. I remind you that EuroCirCol is a design study supported by the European Commission, but it is also, and mainly, the core part of the FCC-hh project. The program was funded for 4 years, and it comes now to the end with its final report. So that's what we are being presented. The next talks will summarize the great work which has been achieved and which is also an important, or should I say, essential part of the FCC, of the entire FCC design study in general. So the first speaker is Barbara Dalena from CEA, and she will explain us what has been achieved in the work package 2 and 3, which is the lattice design and the interaction region. Your turn.
Good morning. I have the honor to present to you. Can you hear me? Okay. Now it's better?
Yeah.
Okay. Can I have the slides, please? Okay, thanks a lot. So I will present to you the FCC Hadron-Hadron Accelerator design on behalf of the teams that is made up of 15 European institutes and many more people. The circumference of the ring has been fixed at about 98 kilometers. It has 8 straight sections here. 6 are 1.4 kilometers long, 2 are about 3 kilometers long here. This layout fits the geological constraint given by the civil engineering study, and with the 16 Tesla dipole, it is able to reach the 100 TeV center of mass energy. The arc filling factor is 80%, and the design is based on the separation of the various functions in order to protect sensible device from radiation, like in the LHC. These 2 injections in these 2 regions allow to inject from both the LHC and the SPS. Michael already shown to you that a comprehensive concept and design report is now available and will be presented later. Here in the slides, I summarized some of the main parameters of the beam. These parameters are able for the first years and with the initial configuration to reach the same peak luminosity as HLLHC, as you can see here. The last 2 parameters of this table already define which are the challenges of this machine as compared to the LHC and the high luminosity that needs to evacuate 2.4 megawatt of power coming from synchrotron radiation photons and to handle about 8 gigajoule of stored energy in the beam. The integrated luminosity of 30 inverse Antobar is required for the physics studies. This, and even more, can be achieved with an optimum time in collision of 3.7 hours, a turnaround time of 4-5 hours. And as you can see here, in both collision scenarios, at the beginning, after 1 hour, the luminosity is enhanced due to the shrinkage of the emittance from synchrotron radiation, while after this optimum time, the luminosity falls down very quickly due to burn-off. The detector length in the 2 high luminosity insertion region is about 50 meters. What you see here is half of the detector, while the cavern has a total length of 60 meters, and the additional length is required for both the opening of the detector and the forward shielding that catch the backscatter particle from this copper absorber here. Other 2 meters here are required for the vacuum, and this altogether fix the minimum distance of the first quadruple of the machine with respect to the interaction region. The design of this first quadruple together with the other 2 made up what we call the triplet, the last triplet of the machine. Its design has been optimized in length and shielding according to the space available in the straight section. The present design allows sufficient aperture. Here you see the 2 beam envelopes for the nominal parameter, the 0.3 meters beta star, but also allow to accommodate even further optics. Space for cavity is reserved here after the separation dipoles, and the maximum voltage of 13.4 megavolt has been estimated to be required. Dynamic aperture is above target if a good phase advance is chosen between the 2 IP, and nonlinear corrector are required above all for very pushed optics. An alternative triplet has been also studied with a systematic scan of the design parameter phase in order to find the shortest possible triplet compatible with beam stay clear and shielding, with the aperture and the shielding. And here you see the parameter. It includes also flat optics. The advantage of flat optics is that they need less crossing angle, so less crab compensation. But for the same dynamic aperture, they need larger separation according to the beta ratio due to long-range beam. The 2 low luminosity insertion are combined with injection, as is done in the LHC. At the moment, there is no target luminosity for these 2 sections. The present design can achieve 10 to the 34 with a free distance between the accelerator and the interaction point of 25 meters. The triplet design is similar to the high luminosity injection, but of course is less challenging, having reducing luminosity. And in particular, here the 2 separation dipole have been chosen to be superconducting, so a more compact design is possible. Concerning the injection, it is made up of 3 half cells, 150 meters long, in order to host the 3 injector devices. Other 2 cells are added between the injection and the experiment in order to add further protection device. As I said, the triplet have been optimized for the shielding. This shielding is needed in order to absorb the collision debris coming from the proto-proton non-elastic collision. And a comprehensive study has been done from the triplet to the matching section in order to study this. Here you see the integrated peak dose in the triplet. These are the 3 quadruple magnet. And as you can see, in case of vertical crossing, the peak dose can be quite high with respect to the present limit for radiation dose. By the way, alternatives have been explored, and here you see that the change of crossing plane and polarity up and down can bring to the green curve, which is already better than the red one. Also, the splitting of the second half of the Q1, this part is a zoom of this, is able to bring very close to the present limit this. Additional collimator are instead, and masks are proposed instead for the matching section. Also, the possibility that photon from synchrotron radiation coming from D1 and D2 and hitting the central part of the detector has been studied, and simulation shown that this is not an issue. As well, muon crosstalk between two IPs is not a concern, while 50 centimeter long mask is required in order to protect the first quadruple in the dispersion suppressor, that is after the collimator in the dispersion suppressor, from the shower coming from inelastic proton losses on the collimator. The extraction insertion has been designed as well. It has larger beta function, that means also beam envelope, that is plotted here, at these two absorbers. The extraction kicker is highly segmented, and a sushi costita septa has been chosen to extract the beam in the vertical plane. Here you see the beam on the dump, the pattern of the beam on the dump. The main issue here is the dilution kickers. The collimation system has been scaled up from the LHC1. Here you see the design, and in green you can see the position of the collimators. But unlike LHC, only horizontal and vertical primary collimator have been considered for FCC. And also additional collimator are placed in the dispersion suppressor, experimental, and extraction insertion. The beams clear the aperture of the machine are below the protected aperture for some cases, but this is not considered an issue since this element can be redesigned. Energy deposition studies have been shown that power on the primary collimator can be reduced by halving the active length of the collimator and removing the skew primary collimator. And the power on the first secondary collimator can be optimized by increase the thicker of the jaw. A redesign also of the dispersion suppressor collimator is being considered in order to withstand the secondary shower coming from the losses on the collimators. The thermomechanical simulation shown that in general collimators survive the losses, but still some issue on the plasticity on the cooling pipe, for example, needs to be solved. Concerning the local inefficiency, at both injection and collision, the power load from the horizontal and vertical losses is below the quench limit. As you can see here, what you have to look is for the blue, which are losses in the superconducting magnet that can be damaged from these losses. They are well below the critical limit that is somewhere here. Also, the off-momentum halo beam at the start of the acceleration ramp is below this limit. Concerning the RF will be similar to the LHC, the same frequency. The installed voltage is 48 megavolt, 42 are required in collision to provide stability, and 12 megavolt is chosen for the injection. Concerning the design of the insertion, it's made up of photo cells of 72-degree phase advance, which is a compromise between the beam stay clear and the maximum gradient of the quadruples. In this insertion, space for feedback, electron lens, or RF quadruple is foreseen. Here you can see half of the arc cells with the dipole, the quadrupole, the sextuple, and also linear and nonlinear corrector. It has been the results of optimization coming from iteration given by different constraints, civil engineer constraint for above all the length of the arc, magnet maximum gradient and field quality, the beam screen, the possibility to integrate correction scheme required for the experimental insertion, machine aperture, and beam stability, so the need to install Landau octuple for damping stability. The matching of this arc cell to the insertion is done with the dispersion suppressor. It is of the same type of LHC. The main constraints here are given by the maximum beta function, dispersion, phase advance, which basically are required to obtain the machine aperture. The fact that we had to host, to reserve space for collimators and masks. Concerning the definition of linear and nonlinear correction scheme, differently. We have, of course, used the scheme of LHC, but unlike LHC, some of the correction can be done only in the long arc and not in the short arc, where the number of cells is very small. Also, the choice to use niobium tie technology for the corrector forces to have to reserve much space for correctors. The performance are driven by the field quality and the alignment of some specific element in the machine, mainly. The possibility to build up electron cloud has been also studied. Results show that a secondary emission field of below 1.2 is required for the 25 nanosecond bunch spacing. The most critical element is the quadruple, and around 1 for the 12.5 nanosecond bunch spacing. A baseline scenario for the mitigation of the electron cloud has been worked out. It consists in using amorphous carbon coating, and as you can see here of the beam screen, in the dipole, the electron density develops differently with respect to the quadruple. So the idea is to add this coating in the beam screen at the top and the bottom for the dipole, and at 45 degrees for the quadruple. Also, a laser-treated surface mitigation technique can be interesting. I consider as alternative. And finally, the sawtooth here in the beam screen that have been designed by the vacuum group to reflect back in the antechamber the photoelectrons emitted by synchrotron radiation are better also for electron cloud. Now, the coupled bunch impedance here and the single bunch impedance, effective coupled bunch and effective single bunch impedance have been calculated based on the weighted dipolar impedance. They allow for a comparison of the effect coming from the different element in the machine. What you can see here, the results are that for the frequency that are important for the coupled bunch instability, the elements that dominates the impedance budget are basically the resistive wall impedance of the beam screen at both injection and collision. Instead, for the single bunch instabilities, The situation is different between injection and collision. At collision are mainly collimators, while at injection also interconnects and the beam coating plays a role. Among the ongoing work on the impedance, there is an experiment that aims at measuring the impedance of beam screen coatings, different beam screen coatings. Sorry, it's different, the plot, by the way. During operation, the couple bunch instability, above all the mode 0, is expected to be 3-4 times higher in FCC with respect to LHC, while the stability region provided by the Landau octupole is expected to be almost the same. So the strategy here is to use active stabilization by transfer feedback for the mode 0. And here you see in green the mode 0 damped by the feedback, which is the same type as LHC but scaled up in frequency, and to use Landau octupole only for the higher mode. As you can see here, the first mode, and here the stability region provided by the negative octupole polarity. When there is the collapse of the separation bump and the two beams start to collide, this stability region here shrinks because there is an interference with a long-range beam-beam interaction. So here the solution has been found to collapse the two beams at 1.1 meter beta star, because the reduction of the stability region is few percent, and to collide the two beams during squeeze. Also, alternative to Landau octupole have been studied. One consists in RFQ quadrupole, and here you see the relative electric and magnetic field. It can help to reduce Landau octupole current, or a few of them can stabilize the beam alone without octupole for Landau damping. Electron lens as well have been investigated, and here you see the stability region in this case. 140 milliamps are enough to provide Landau damping for the mode 1 at fat top. Beam-beam effect has been studied, and a total tune shift of 0.03 has been found to be feasible, having the full cancellation of the crossing angle and asymmetric phase advance between the AP. As you can see here, the loss rate due to the beam-beam at 0.3 is still quick. The add-on beam-beam generates also beta beating that needs to be considered in the beam stay clear computation and in the correction scheme. And finally, what we see before, that negative octupole polarities and long-range beam-beam gave is not good for beam stability, is instead preferable from dynamic aperture point of view, because provides enough aperture. The FCC will be used also as a ion-ion collider with the same optics like in LHC. Parameter and luminosity estimate have been done for the the lead-lead and the proton-lead species, and are reported here in the case of 1 experiment or 2 experiments. And also they have been evaluated for other species. Here I just reported one. The performance in this case are driven by the quality of the injectors, and the key issue here is the high flux of modified ions that come from bound free pair production or electromagnetic dissociation that you see here. Their envelope can hit the dispersion suppressor collimator, likely, but they produce from fragmentation shower that then needs to be absorbed. Also, the design of the injector has been looked at. For the 3.3 TeV injection energy option, the LHC can be used as an injector with 5 times faster ramp. And for the 1.3 TeV injection energy, the superconducting SPS is feasible, but presently excluded by dynamic aperture. The transverse line have been designed as well. Here you see the sketch from the LHC and the SPS. And the main issues here are protection against machine failure. To conclude, a working conceptual design report for the FCC Hadron-Hadron machine exists. It shows no showstoppers. Several alternatives for the different functions of the machine have been studied as well. Challenges have been identified with possible R&D to be followed up, and still room for further optimization is possible. So you are very welcome to come tomorrow to all the session and discuss with us. Thank you very much.
Thank you. Thank you, Barbara. So is there any question? We can have a few questions if you want. No, I don't see any hands. You were very clear. You said the aperture has margin. Mm-hmm. I don't remember if I've seen any numbers there. What is the aperture of the magnets?
Okay, so in order for the collimator to work, we set an aperture margin at 15.5 sigma, more or less, and which is the gray shown here. As you can see, the two envelopes of the beam in this region are well below this limit. And so this means we have sufficient aperture margin in this case. Okay. Also for the rest of the machine.
And also except a second point?
Except some point in the collimator, where, by the way, by redesigning this part can be solved. This problem can be solved. Here, the aperture is the red, and what we say is safe is this green line.
Also, you said for the injector that you will use the LHC, this is the baseline, with 5 times faster ramp. So what does it imply? You can do that with a present magnet?
Maybe Brenner is here, can reply better than me. But I think that already you don't go up to the whole energy of the dipole can reach is 3.3 TeV. It's not 7, okay. 6.
We gain a little bit there.
Then I think there is also something else, but at the moment I don't want to say wrong things.
Yeah, you may have to change the circuit layout to, yes, but this has been studied in this also document.
Okay, so thanks again, Barbara.
You're welcome.
And we move on with the next speaker, who is Francis Perez. Where is he? Oh, you're here. From Alba. So go ahead.
Sorry, small technical issue. I wanted to have the PowerPoint, and he gave me the PDF. So some animation are not there, but it's fine. It's not a big deal. So I will talk about the EuroCirCol project, about the ball package 4, which is the design of the beam vacuum system, as you have seen before with Michael and the previous speaker, Barbara. So the charge of the ball package 4, I went into the PDF document that was our project, and it was the cryogenic beam vacuum system conceptions. And I read here some words. And there were some words, I mean, synchrotron radiation, beam-induced heat load, vacuum instability, photon-electron impedance due to the image current, cooling, everything, and to be mechanically stable. So it was a big challenge to comply with all the requirements that such a system has to require. And this was our charge as a work package 4. For that, we just divide the work in several tasks, of course. I mean, some coordination, otherwise we will not be able to fit together all these works. We have also to study the beam-induced vacuum effect. This is the main aspect. We have a vacuum chamber. We want the beam to be stable, and to be stable, we have to analyze the vacuum effects of the beam. Because the beam vacuum effects, we already knew we have to study mitigation techniques for electron clouds and study mitigation techniques of instabilities. Also, we knew for the cryogenic heat load we were required, we will not be able to work at the temperature of LHC, so we need to work another range of temperature, 40 to 60 Kelvin, and this requires, we need to study an area of stability which was not foreseen or have not been studied before. And all of this has to match with a mechanical, according to our charts, was conceptual. You will see at the end, I think we just skip the conceptual, we have a completely mechanical design done. So I think we haven't even gone further of our charts. And to check again all these things, prototyping and measurement were foreseen, and this is what I will try to show you here in few words. This slide has been presented in all the previous FCC weeks, but I have to present it again, because we have a challenge, and the challenge is a synchrotron radiation power density that is more than 100 times the one we have at LHC. You could see here the number of the LHC, 7 TeV, and you have the synchrotron radiation load 0.2 watts per meter linear of accelerator. And what we have in the FCC-hh is more than 100, almost 200, 150 times higher. And not only that, also with critical energies, which were beyond by a factor 10 of the one we have at LHC. And still, we require a very tight gas density to allow the beam to be stable and to have good lifetime and to avoid nuclear gas scattering elements. So E clouds, as was mentioned before, and heat load synchrotron radiation as before. So, more or less what I say. So this is high power density. That means we will require to think of the vacuum system with a much more flow of gas to being able to cool factor of 100 more power. We have to define the beam screen that should work at a temperature 40 to 60 Kelvin, not in the 5 to 20 Kelvin that was foreseen, and we have to analyze how the gases behave at these temperatures, what is the equilibrium pressure of these gases. And because the extra photons, so photon destruction is higher, we have to have high effective pumping needs. So the consequence of this is that the LHC vacuum chamber is not adapted to our needs. And I went back also to all the slides, and this was in March 2015, so already more than 4 years ago, and this was our first idea. Now it seems a little bit silly, but this was a breakthrough idea of how we will do it with it. And the breakthrough idea is that here we have a single screen, and here we started to think of a double screen. So a vacuum chamber and the screen of this vacuum chamber. So it's the vacuum chamber, okay, vacuum, and this makes the screen to protect the core bore. That's also was, you will see later, okay, that was the first idea. Of course, this idea was not good enough, first, because the asymmetry, okay, depends on how you go. Because immediately afterwards, we realized that if we want to make it stable from the point of impedance, it has to be symmetric. So we went quite fast to a symmetric design. We have, this is to reduce the impedance. So we just had a lot of think about heat transfer, and you could see the first slide has copper outside to spread out the heat load around the chamber and be protective. We need hyper-pumping steel, so we will increase in the hole. You cannot see here, but here, biggest hole. And we also have to go through thinking of how to manufacture it in a proper way. So we have been several going around, and then this has been the several designs. And you could see also we make a design to forget about the dip, and we went into the sawtooth, which we believe was most important. And you could see how from the very first shape, we have been evolving to a very simple thing. Simplification was important to make this feasible, to make it this realistic to be done. And let's say we have now the latest version, which has very small changes with respect to the previous one, but changes important from the point of view of the constructions and stability. And this is how it will look like. These are the design where we assume here laser-threaded or carbon, amorphous carbon, sawtooth, a screen with copper, big pumping holes, and I just invite you to go to this seminar to know more about the things. And this is how it has evolved. This is LHC, and this is our latest design. You could see it's a scale that has been even more challenging. We have to fit even in a smaller cryo tube. So, and these are the pumping holes. Now we have big pumping holes protected by this screen, which then are transparent for the beam, so it's transparent for the impedance. We have increased with that the pumping capabilities by a factor 5 or 6. And we have been able to cope on this area with the sawtooth and all the cooling. You could see the size of the cooling channel and the final size of the cooling channel to cope with more than 100 times more power emitted here. You will see that laid up. Yeah. And now, all right. So, but the important thing is that this screen is capable of sustaining the circular radiation, the heat load, but also is able to procure a good vacuum into our machine. And this has been thoroughly studied by Ignasi. It has been a long study which takes into account photo-simulated, electron-simulated, ion-simulated photodesorption, how the vacuum affects, has been in close collaboration with Board Package 3 in impedance aspects, just to know how much, and not impedance, electron class computations to make sure that things were compatible. And the good news, and this is just my message here, is that according to the computations, and you could see here what is expected, the density or the vacuum to go down, the gas density, with respect to the accumulated dose during operations, and one can see that when we will reach the 100-hour lifetimes in around 3 to 4 months commissioning, which is very reasonable. Analysis of what has been the different things of that. There is an important aspect which has been hidden, and you will be able to see in this presentation by Ignasi on Wednesday. That is the fact that we are using the interconnection of the Wendling magnets to really absorb a lot of radiation. So you could see how the vacuum is quite stable along the magnet, and then in the connection you have the big bump, because here is where we place a specific absorber to just catch much of the power. To achieve this resource, which means this one, which tells us the system should be feasible, we have, of course, worked a lot on the different tasks as an input for these tasks, and I have stated that this has allowed us to to increase our understanding of the materials and of the technologies required and of the computations that we have. So one of these things has been the study of the mitigation techniques, in this case, the laser ablation surface engineering, I believe, I hope, Oleg, where they have made more than 100 samples of using different kinds of lasers to be able to determine the best option or to be able to characterize the process to be able to understand how better to fit with the requirement of FCC-hh. So they have been also studied how much thermal gases will occur, no problems occur, the effect on the secondary deal, and also the problems of the UFO problems, so small particles that could be capped in within the small grains here. So to know more about the progress that has been done on that, I just invite you to the talk of Reza about the laser ablate surface engineering and how much this could help in technology advance. In parallel, also because we have to have our plan B, studies on neck coating has been analyzed and has been studied as well, how it works at creating temperatures, how it will happen with synchrotron radiations, and also which new kind of neck coatings we can apply that could just be the best options for the previous one's questions. So this has been, a study has been crucial just to understand in which way is better to go. The other aspect, as I said before, we need to have it, the vapor gases, so that we are working at different regions of temperature. So here is where normally LHC works, in the low temperature range. Sorry, let me see. Yes, here. So it's a stable, gas-stable area. So either the gas is out of the surface or it's absorbed by the surface. But when we just go over around 20, I don't know the number exactly, it becomes difficult to know if you are stable or not with respect to the gases. And then this is one of the tasks that has been doing. So they study the vacuum stability at this range of temperature, just to be sure that in between the area 60 Kelvin, the gas state that is absorbed in the surface or either is disadsorbed and then can be pumped. So, but not coming up and down of the surface, which will be completely complicated to deal with normally with ring injection or ramping. And a lot of studies has been done. This has been done in the Frascati with copper as along, with copper treated with lasers. And we have seen that there is some challenges to be understood, and there is some aspect that has to be taken carefully before applying that without thinking. So to know more about these results, again, on Wednesday, Luisa will explain all the studies has been done there and the importance of the different compositions and the different structure on the laser surface, just to comply with the specs. Last but not least, that's what they say. We make all these studies, we make all these computations, and it's needed also to prototype and to understand and to measure if this is really achievable. If what we are thinking in the small lab, a small sampling, if what we are thinking in our models can be translated into a real setup. So since the beginning, we just wanted to make prototyping and measurements, and we are using CARA, the synchrotron light source, which is in KIT, Karlsruhe, and there we place a setup where, you could see it here, a setup where a 2-meter-long prototype can be installed and can be irradiated with synchrotron radiation, and then studies can be done. Why CARA? CARA has if you look at the emission, synchrotron emission of the FCC-hh, a 50 EV, is this one, a 50 TeV, sorry, and you see the CARA synchrotron radiation emission, you could see how much it matches. So really, it's a matching thing with respect to the future FCC-hh. So we did 3 prototypes. You could see this is the second one, I believe. This is the second one with the electrode erosions, and we have 3 prototypes to study different effects in each of them. So the validity of the you can see here the deflector, here to make sure that the photo emissions can be measured. We put an electrode just to measure the electrons that are photo emitted from the synchrotron radiation impinging in here. And this one, the third prototype, after we have already analyzed the results, and that's the conclude that sawtooth will be the best one. And this is similar to the final decision. Everything, if you look carefully, the vacuum pumps are smaller than the one of the final design. And this has been already studied. So data of all this has been done. You have irradiated the chambers with synchrotron radiation coming from the Cara beam with similar spectra than the one we expect at the FCC-hh, and we have made several analyses of the conditioning time on the different dose rate. These, let's say, unique studies of photoabsorption that has been done at Cara will be presented on Wednesday in the session of the EuroCirCol board package 4. This has helped us at the first step to know that the system is, to check results with the modeling. So this also has allowed us by computing this loss, and by checking the ratio within the different gas species, we have been able to really refine our models that have been applied beforehand. And this has to be stable. So the vacuum chamber that has to comply with all these requirements has to be stable. So a full mechanical design has been done. So quench analysis, thermal analysis, even we have already solved the way we will install it in the cold bore has been analyzed. So for that, please, again, go to this talk, which will tell you much of these studies and much of these complications. Also, this has required many iterations just to make it stable, because it has to be what we have been always looking for: easy manufacturing, stability, and, let's say, simplicity. As you can see, has become much simpler than the first design. And not only that, we have gone further, and then we have started thinking how to build that in a mass production. So already we have been designing this kind of machine by thinking if it will be possible to do it in a mass production, just to make sure that we will be ready in case FCC-hh is approved. So go to the poster about consideration for large-scale production of the SCC beam screen by Cedric, and he will tell you his ideas about how to make these things hundreds of kilometers in an easy, let's say, and feasible way. And I have to say, this was World Package 4 somehow, but I want also here to mention something. One of these projects, this is financed by the European Commission, and this is always very good. But when you put together people, you know something happens, and happens that collaborations grow. And I want to mention few spin-offs collaborations, not companies, that come out from this collaboration. So this has been collaboration that could not have happened without EuroCirCol World Package 4. One of them is, I talk about photo distortions and things like that, but also at the quite beginning, Roberto Cimino pushed us to think about reflectivity. In fact, the incident angle of the synchrotron radiation in the screen is so small that, in fact, most of what happens is reflections. And that's why we put the absorbers in between the magnets, because 90% of the photons goes in between the magnets. So to study reflection was an important issue. And this was, I have to say, gone further of what was intended initially, and we could be able to also measure reflectivity and photon yield for several candidates, together with some beam time at BESI, which are very nice experiments to study the reflected radiation, not only the absorbed radiations. And for that, go to this talk of Roberto Cimino, where results has been used. And these results have been applied later to our modeling to be able to assure that we were on the right track. Also, because we have realized that this photo absorption and these reflections is a critical issue. I mean, a new setup is going on, and this will be done. And this is the windy setup at Frascati lab of ANFM, where they will use Daphne and the UV, ultraviolet radiations coming from darkness into some beam lines, and they will use 2 beam lines that I already have for small samples, but they will aggregate it for a windy, which means white light line for desorption yields, which will allow to make this test also in long samples, because we want to make sure that there is not a scaling problem. So whatever we measure in small samples can be also extrapolated to long samples and to analyze it. So this is also a spin-off, and we will continue working on that through a collaboration with CERN, and to know also data about that. Marco Angelucci will give you some data about this windy setup at the LNFM in Frascati. And another one, which is quite challenging, is we have been thinking, because our colleagues from ball package 3 was telling impedance, resistivity, and all these things. And that was always a kind of thing, okay, you know, copper has a given resistivity, how to improve it? And with our colleagues, in fact, ICMAP, Teresa, was pushing with Sergio Calatroni a lot for new ideas, and we went to the idea of using coated conductor high temperatures coated superconductors to be able to coat the vacuum chamber and to drastically reduce the impedance. Is that right? In fact, we didn't know, because even though superconductors are perfect conductors at DC, it was a big question mark if superconductors be perfect conductors at the range of frequency that the beam will induce on it in the vacuum chamber. So we have to ask, okay, what is the resistivity of these superconductors with respect to the frequency? As a function of the temperature, 40 to 60 Kelvin, as a function of the field. And we didn't know. There was no answer to that. So this was a project that was launched. And in this project, we want to see the feasibility of this technique for the vacuum chamber. We have developed a technique to measure the surface resistance as a function of the magnetic field after the temperature, and we have been able to measure it up to 8 gigahertz, 40 Celsius, 40 to 6, okay, from cryogenic temperature from 10 to 100 Kelvin and up to 9 Tesla. And this, I think, we will follow up. Also, we have installed one of these layers in a synchrotron radiation at ALBA. We have irradiated it with synchrotron radiation while at the same time measuring the DC resistance to see if the synchrotron radiation will damage the superconductors. And the first results, repeated several times, but we could not believe it, is that we can irradiate it with no beam, with 100 milliamp, with 200 milliamp, with no beam again, and the DC curve maintains the same behavior. So for that, a lot of work has been done, and there is a couple of talks by Patrick and Arthur, and a couple of posters by Patrick and Geoffrey as well, which tells you about these new developments. So as a conclusions, I have to say we have gone through many iterations to be able to accomplish our goal, but we believe the beam screen is mostly completed conceptually and almost things. We have come out with the needs of a dipole and photon absorber. I haven't explained much later, but if you want to know more about it, go to the Ignacy talk. We have made several prototypes, and we measure it on the Cara Bestex setup, and upgrade for doing measurements at liquid nitrogen is in the progress. We have optimized, or we have been working a lot with laser treatment to optimize it. We have studied the gas association effects very efficiently, but we haven't finished. In fact, when I asked my colleagues what much is needed to do for the R&D, of course, we need to further study the effect of the light into the surface as a function of temperatures very close to the temperature of the LSC, and this is Cara Abectes, and also we will use windy at Frascati. Even though our computations tell the vacuum chamber is stable, we need to test it, so we have to be able to make sense of this 2-meter prototype and things, and seriously check the mechanical testivity. We want to further optimize the large-scale productions. As I mentioned before, we want to investigate other surfaces just to be able to be prepared in case, you say before Barbara was complaining that the resistive wall impedance was the problem of multi-bunch instability. So if we want to really catch this problem of the multi-bunch instability, reducing the impedance resistance is a must. And with all that, we want to improve our computational model to be much ready. And there are sure, more ideas to come. So I will say that the charge that was given to us at the beginning of the project 4 years ago has been successfully done. And I have to thank for that a lot of people, and I hope I haven't missed someone, but if I missed someone, I apologize. So I thank the team that really did all this work, and I thank you, of course, for your attention. Thank you.
Thank you, Francis, for this fantastic achievement. This is a great job. Any questions or comments that people would like to add? Our speakers are very good. I mean, you mentioned the coating.
Yes.
Do we need to coat the beam pipe over the 100 kilometer?
We need to coat the beam pipe. I mean, if we are talking about electron cloth, we will coat it selectively there where we need it. That's clear. When we're talking about resistive wall, one can think, I mean, you have to reduce the resistive wall, so you could think in clever ways to reduce it without being able, but you will have to mostly coat the 100 kilometers, yes.
Okay. So thank you very much, Francis. That was very clear and very successful. We move on with work package 5, and this is the 16 magnet Tesla R&D for 16 magnet Tesla. 16 Tesla magnets, sorry, I can't spell. So this is Davide Tomassini from CERN who will present the work done in this work package.
Ladies and gentlemen, good morning. So I will summarize the activities performed within the EuroCirCol on the 16 Tesla magnets. And the talk will be composed of 2 parts. The first part will provide a general overview of the program. And the second part will be presented by Bernardo Bordini and will summarize the evolution results of the conductor program, which is also part of work package 5 of the EuroCirCol. So I'll go through an overview of the what happens? The laser, is there a laser pointer? The big button, of course. So I will spend some words about the impact of this program on the magnets community, the contribution to the FCC-hh. Then I will spend also one slide on a special deliverable, which in reality comes from the US Magnet Development Program. The US colleagues are not beneficiaries of the EuroCirCol, but they are participants. And then I will summarize a number of recent initiatives which in some way they are also a sort of spin-off of this program. So for going up is this one. Okay. Okay, so basically on the 16 Tesla magnets, we have the EuroCirCol program, for, which has the CA, CERN, CMAT, the University of Geneva, KK, the NFN Italy, the Tampere University, and the University of Twente as participants. Then we have a CERN centralized program, the FCC 16 Tesla Magnet Development Program, which supports also economically the conductor development and procurement, an R&D activity performed mainly at CERN, but also elsewhere on magnets, and an activity on model magnets. And then we have a companion program in the United States, the US Magnet Development Program, which is initially focused on the manufacture and test of a 14, 15 Tesla cosine theta magnet, on the exploration of candidate cosine theta configurations, and on novel diagnostics and advanced modeling techniques for magnets, for quench, for instrumentation. I am really proud of listing a number of points that I feel extremely important as the impact that this activity has produced in our community. First, we have set the parameters for the conductor and the magnets. And this has been an extremely important step because worldwide, these parameters have been used as a basis for launching internal programs. The choice of then we have also decided to choose certain specific activities as activities of general service in some way for all the individual directions that we purchased for these magnets. For example, for the quench protection, for the conductor characteristics, and also for the analysis tools. And this has favored the interchange between laboratories. Also, we gave a lot of importance to the sharing of information, and this had an avalanche effect across the generations, from students to senior scientists. And in this respect, we have the whole community has put in place an enormous effort in having continuous meetings, sharing of information. We had about 40 collaboration video meetings, about 30 topical meetings, and many of them, I would say even most of them, with a larger participation from not only European laboratories, part of the EuroCirCol, but also from the US labs. So first, we contributed to the definition of the FCC-hh. I will not go really in detail of this work, but I would like to say that by really working together, we understood that it is not true the classical, let's say, idea that, okay, until 12 Tesla, you do cosine theta, above 12 Tesla, you do block coils, and so on. We understood that when you do a proper design, considering all the aspects of the design, and hopefully a proper manufacture, then any design on paper can work. And this is extremely important, and we will see later how much it is important. And also, this is a special contribution of Saclay for the quadruples. So in this frame, we also decided that one of the deliverables of the EuroCirCol program had to come from the US. And we selected this one. Maybe we were already looking into some future. I will come to this. And this is the manufacturing folder for a reference design of a dipole shore model. We decided to take this result from the US Magnetic Development Program because at that time it was the most advanced, but also because this is let's say 99% is a US work, but this was really discussed in a wonderful atmosphere within the collaboration. At the point that CERN even decided to provide a symbolic, but still a contribution to this program through a number of initiatives. So, as a spin-off of the EuroCirCol, we also are having a number of initiatives. We have signed with the CA-hh a contract for an agreement for an R&D activity on high-field magnets to be performed in CA with the aim of building a demonstrator for the FCC. We have also signed an agreement with the CMAT, which initially will go through the build-up through a reinforcement of the laboratory in Madrid for making niobium tin magnets, and with INFN, Milano and Genova, also for making a demonstrator of an FCC-type magnet. Also, CERN has signed another agreement with the Swiss Confederation to launch a program for creating a pole of an expertise of superconductivity beyond the existing one. We should not forget that in Geneva, there is the University of Geneva working mostly on the conductors. Then there is the EPFL and PSI. But we wanted really to favorize a bigger laboratory of superconductivity in Switzerland. So the latest news, we have completed the manufacture of all the parts in CERN for a demonstrator magnet potentially capable of achieving 18 Tesla. But this is not an accelerator magnet. This is a magnet made with the racetrack coils, which is made to understand the processes, the mechanisms in the region of the very high fields within the limitations of the niobium tin superconductor. So we made the coils, the magnet, everything, and then now we have to assemble the magnet and hopefully to test by the end of the year. Another important news is that the dipole magnet, the cosine theta dipole magnet, which has been mounted in the US, which is the object of the deliverable of the EuroCirCol I mentioned before, has been now tested. I decided not to show any graph about this magnet because I would like to give the honor of our US colleagues to present this. This magnet places us already in the future. This magnet did a training at 1.9 Kelvin. It is an accelerator magnet with an aperture of 60 millimeters, even bigger than the one needed for the LHC. The training at 1.9 Kelvin was stopped at 14 Tesla because the magnet was assembled to not exceed 14 Tesla for a prudent choice in the mechanics. The magnet made a thermocycle, and then at 4.5 Tesla, as it was stopped for mechanical reasons in some way, it was then retested at 4.5 Tesla. Until 14 Tesla, it did not quench. So the magnet exceeded 14 Tesla. So they did one quench just above 14 Tesla and then stopped the test for then reassembling the magnet with a bigger stress in order that it can go to a higher field, or it may get damaged. For me, it doesn't matter. This is a record magnet and places us already in the future. So the second part of the talk will be given by Bernardo. Thank you very much.
Okay, so I propose that we ask questions at the end of the both talk. So.
Good morning, everybody, and thanks to organizer and to Davide for giving me the opportunity for summarizing the main results of the EuroCirCol conductor program. One of the major challenges for a 16 niobium-13 accelerator magnet is the conductor behavior under large transverse loads. Indeed, for an optimized magnet, the pressure on the conductor is proportional to the magnetic field. So for a 16 Tesla magnet, essentially we are talking about a pressure in the range between 150 and 200 megapascal. This sketch here shows a cross-section of a cos theta 16 Tesla magnet for the FCC. On the top, you can see the field map, and on the bottom, the calculation for the mechanics, where you can see that on the conductor, when the magnet is energized, reach a level of pressure of 180 megapascal. Why this is critical, why this is challenging? Because niobium-13 is a brittle material, and the superconducting performance are strongly dependent on the strain state. On this plot here, you can see the behavior of a critical current strand under axial strain, where you see an increase initially of the critical current and then a sudden decrease of the performance. While the behavior of the conductor under axial strain is well known in the community, well established in literature, not much data were available before starting this EuroCirCol conductor program. So what was the knowledge before starting this program? First of all, I have to say that the conductor we studied in the program is the typical Rutherford cable that is used for accelerator magnet, based on a round wire. In this case, is powering tube technology, niobium-13 conductor. And before the study, we measured at CERN a Rutherford cable based on these pit wires and a few wires at the University of Geneva under transversal load. The results were interesting. We found a significant reduction of the critical current and the reduction of the upper critical field already at 150 megapascal. However, the limited data available, the complexity of the experiment, the fact that only the pit technology was measured did not allow drawing general conclusion, also because there were other studies in the literature showing that the effect of transverse load on the conductor up to 200 megapascal was limited. On the other hand, if the data by CERN would have been confirmed, this would have a significant impact on the design of a niobium-13 accelerator magnet. So for this reason, in the framework of EuroCirCol, we decided to launch a campaign of measurement coordinated by CERN with the University of Geneva and Twente to try to understand the following outstanding question. Are the CERN measurements reproducible, and are these results reproducible in different setups? Can we extend these results also to the other main technology for producing niobium-13 wire, the restacked rod process superconductor that is used for the HiLumi project? At which pressure we observe permanent reduction of the critical current in cable test? And finally, why wire measurements show larger sensitivity to transverse load with respect to cable measurement? To address this question, essentially we prepared a campaign of measurement, and the point of reference of this measurement was a 10 millimeter wide Rutherford cable based on 1 millimeter wires, which is the same cable that was tested previously at CERN. Both CERN and Twente University measure each 2 cable samples made with the PIT technology and 2 cable samples made with the RRP technology. And the wire using this cable were measured at the University of Geneva under transverse load, the same wire used in this cable. And we measure a round sample and also 15% rolled sample. The rolled sample are sample prepared to mimic the mechanical deformation that the wire experienced during cabling. So we wanted to see what is the effect also on these rolled samples. Okay, these slides I briefly presented the different setup used for this study. This is the sample holder developed at CERN for measuring test under transversal pressure in the Fresca test station. The characteristic of this setup is that it's very representative of the conductor behavior in a magnet. Nevertheless, the contrast of it is that it requires a long test campaign and only a relatively narrow cable can be tested at very large pressure at the level of 250 megapascal. The second setup that we used is the one at the University of Twente, where we have a superconducting transformer, and we have essentially we can put on the sample at cryogenic temperature very large pressure on it. And the advantage of this setup is that allows rapid test campaign. On the other hand, the contra of this setup is the fact that we can only measure relatively short sample, 45 millimeter, which is smaller in general than twist pitch of a cable. And also these cables experience large gradient in field. Finally, the last setup is at the University of Geneva when we measure wire under transversal pressure. The advantage is that there we can put very large transverse load. This is a rapid and economic, allows rapid and relatively economic test campaign. And the contra, of course, is that we are evaluating only the wire behavior while we need to know what the cable is performing. Okay, we'll enter now in the part of the presentation when I show the main results of the EuroCirCol study. This is an example of a critical current measurement done in the Fresca test station for a pit conductor. In here, you can see the transition from the superconducting to the reversible state at different magnetic field and for different level of applied pressure. For this type of plot, from this type of plot, we can extract the critical current of the sample. So these lines represent the critical current of this sample for 3 different levels of the pressure at different peak fields. Where you see that we have a significant reduction of the critical current with the transverse load. And this reduction is mainly due to the reduction of the upper critical field, which means that the reduction is larger and at larger field. For example, at 150 megapascal, we have a reduction of about 20% at 12 Tesla and up to 45% at 19 Tesla. We also were able, thanks to our EuroCirCol program, to demonstrate the reproducibility of the CERN measurement. So we tested 3 similar cables. One was the original one, 2013, and 2 additional pit cables, and we were able to reproduce the results. Besides confirming and consolidating the results, we were able to extend our knowledge. And in here, I show a sequence of a test campaign in Fresca for our pit conductor, when you see that we measure the critical current at different field, applied pressure. And every time we go to higher pressure, we go back to the original pressure to see the permanent degradation on the conductor. And we were able, thanks to this test, also to assess what is the permanent degradation of our conductor due to transfer pressure. And for the case of the pit, the irreversible degradation started around 130 megapascal. This reduction up to 180 megapascal is mainly due to the plasticity of the copper. And while when we pass the level of 180 megapascal, you see a huge increase of the permanent reduction. And this is due to the fact that we start really cracking the brittle niometry tin filaments. But are these results reproducible in other setup? And what about the RRP conductor? So we measured the same cable, the pit cable and the RRP cable at Twente University. And without entering into details, we demonstrated that, the measurement, the results of certain results were confirmed also at Twente. Furthermore, regarding the RRP conductor, we observe a similar phenomena as in the pit conductor. However, the RRP is slightly less sensitive, but this was expected. And in terms of permanent IC reduction, the onset for the pit is around 130 megapascal, while for the RRP, it's 40 megapascal larger. In terms of total critical current reduction at about 12 Tesla, 150 megapascal, while for the pit, the reduction is about 20%. For the pit, it's 15%. The last question we address is if wire measurements show a larger sensitivity to transverse load with respect to cable test. And we answer to this question by measuring rolled sample under transversal pressure. And we observed, as we expected, that the 15% rolled samples are less sensitive than a round wire and are more in line with cable measurement. With the same performance, essentially the same performance reduction is about with a shift of 40 megapascal. And we were able to prove that this difference is due to the stress concentration that we have a measurement of a round wire. So we can now conclude that the rolled sample is much more representative of the cable behavior, also in the terms of sensitivity with respect to transfer pressure. But what was the impact of this study? Essentially, we demonstrated with this study that the reversible reduction of the critical current due to transfer load, it's important, and it has to be taken into account in the design of high-field niometry tin magnets. In this plot here, I show the current margin of an 11 Tesla niometry tin cos theta dipole in its mid-plane. So you see that when we pass 120 megapascal, we have a sharp reduction of the margin. So we have absolutely to take into account of it in our design. Thanks to this study, this study sensitized the magnet international community to this phenomena, and there are now several efforts to account the transverse load in the design of the magnet. In conclusion, The EuroCirCol conductor program, coordinated by CERN in collaboration with Twente University and Geneva University, successfully answered the outstanding questions that were set at the beginning of the study. The effect of transfer load on the superconducting performance have been understood and quantified. The effect is relevant, especially at high field, and has to be taken into account in the design of high field niobium tritium magnets. And there are at present several efforts in different magnet groups to account for the transverse load in the design of high field accelerator magnet. Thank you for your attention.
Any questions?
Thank you for this very interesting, presenting the results of this very interesting study. How dramatic are these results for the 16 Tesla magnet program? In other words, you just say that these results are now being integrated into the paper design of the magnets. Does this endanger the value of 16 Tesla?
No, at present, because this was in the framework of the FCC program, so now we are taking into account all these aspects to calculate the margin of the magnet, and still the magnet design are still as margin to reach 16 Tesla. But still, I mean, we need still to complete all the calculation.
Yes, I would like to add that, for example, just as an example, for the reference cosine theta design, which has been considered in the EuroCirCol study, but I could cite it also for the block coil or the common coil. In a worst case, so taking the worst data from this study of the conductor degradation, we are losing about 3% of the margin, which means that instead of 14%, we go down to 11%. The design is nevertheless being refined to see whether we can recover part of this small loss in the margin. But the design was already optimized from the beginning for getting the lowest dependency on the stress.
Okay. Other questions or comments? Yes.
It sounds a bit contradictory. Davide seems to minimize this effect and say that it is already accounted, but you draw the attention on how dramatic it is. I think you show that you can account for this degradation in the design. My question is, could you do the opposite? So change the design in order not to have this very high local pressure.
In some aspect in the design, this was taken into account. So we try to minimize, first of all, the level of the pressure. So the maximum when the magnet is energized is 180 megapascal. And also, we try to have the maximum pressure where we don't have the peak field. So partially, this has been already integrated in the design of the magnet.
Yes, I would like to add, we are not minimizing at all. On the contrary, we took actions in the design in order to make this effect small, if not negligible.
Does this depend on the design of the, I mean, is it with cosine theta or block or counted cosine theta? Does it make any difference?
With a block coil, it is easier to minimize this effect. With the cosine theta, it is more complicated, but it is possible. And the results coming from the US magnet confirm this.
Okay. Any other comment or questions? If not, I would like to thank all the speakers and the EuroCirCol and all the EuroCirCol members for this great achievement which was done, including spin-offs, as it was explained. And we thank all the EuroCirCol members as well as the support that we got from the EC. And we hope that we will get a new design study with the EC. So now it's the time for the picture. So please, I remind you, when you go out, turn left, go outside the hotel, where is the exhibition, and go in the center of the exhibition looking toward the hotel for the picture. And smile.